This is a pneumatic projectile cannon. People usually design air cannons by guessing the barrel length or copying something that worked before. Because we're engineers, I wanted a way to calculate the best barrel length, not just for perfect conditions, but for real-world use, before I made any design decisions for its construction. So I made a tool that simulates what happens when you open a valve, dump compressed air into a barrel, and push the projectile out. The tool runs that simulation hundreds of times with slightly different conditions, and then tells you which barrel length works the best on average. Inside the barrel, the projectile isn't flying like a bullet through air, it's acting like a piston. The pressure behind it does almost all the work. You could model every swirl of air using CFD, but that detail wouldn't actually improve the design, because the biggest uncertainties are how fast I open the valve, how much friction there is, and how much air leaks around the projectile. So I made this adiabatic model of the system and made a Python solver for it. At every moment, the simulation tracks 4 things: projectile position, projectile speed, barrel pressure, and tank pressure. That's enough to describe the physics that actually matter for this system. One important detail is leakage. If there's pressure, the air leaks, even if the projectile isn't moving. So leakage in the model depends on the pressure differential, not velocity. A single simulation assumes everything is perfect, but real systems are not. So the tool uses the Monte Carlo method to find out the all-around best solution stochastically, meaning that it randomizes valve timing, friction, temperature, and leakage in the inputted ranges and runs the simulation many times. In this tool, you can input the estimated value ranges as well as the fixed values to get this graph which optimizes for barrel length. Each gray dot is one simulated launch. The blue line is the average performance, and the shaded area shows how consistent the result is. The best barrel length isn't just the fastest, it's a compromise between the most reliable and the fastest barrel, with a length that is reasonable. For the pressurized air tank, I used one of these spliced bottle sections. These are actually the same spliced bottle sections which I made in the video where I made the water rockets. These are great because they're good for both water rockets and cannons. For pressurizing the air tank, I used this Presta valve, which I removed from a broken inner tube of a bicycle. I then glued the valve onto one of these 3D printed bottle cap to garden hose adapters, as I realized that it was very easy to glue the valve onto it. I glued it on with 2-part epoxy glue for a strong and airtight bond. The epoxy also seals any cracks and cures quickly, which makes it the best option for this. I decided to use a manually operated ball valve because it's the cheapest, easiest to operate, well enough performing valve type. I estimated that the opening time for the valve is around 150 to 250 milliseconds, depending on how you open it, so it isn't the best in that regard, but it's good enough for what we're gonna use it for. I somehow needed to connect the ball valve to the air tank and barrel, so I designed and 3D printed these 2 plastic adapters for it, with deep socket fits over the valve. I glued these with epoxy to the ball valve to get a strong and airtight seal. One end screws onto the air tank, and the other end can be connected to the barrel using some O-rings to seal it, while keeping it removable. I used some Teflon tape, which I put around the threads of the bottle to seal them, to make them airtight. Because the valve can be screwed onto the air tank, it means that the system is modular, which is useful if the air tank or these 3D printed parts break or something. It's also convenient because I can just screw it off if I want to add more air tanks or change the valve. The cap with the valve screws onto the air tank in the same way. This needed some more Teflon tape because I think the 3D printed threads were slightly deformed, which made the air leak a bit. And here's the final assembly. I then hooked the bicycle pump to the valve to pressure test it and see if it leaks. The tank itself should be able to endure as much as 10 bar, based on some past hydrostatic pressure tests I've done on these spliced bottles. First, I'll test it with this short 12mm diameter, 62cm long barrel, as I had it lying around. This isn't by any means even close to the optimal barrel length, but it's long enough to see if the fire mechanism even works. It should push the projectile to a decent velocity anyway. And here's the completed cannon assembly with the short barrel. I also think it looks cool, and it's really easy to operate, as you just have to turn this handle right here to open the valve and launch the projectile out of the barrel. For the projectiles that this cannon is going to launch, I designed this cylinder with a rounded end and a hole in the bottom, which I'll print out of TPU filament, because it won't shatter and impact in the same way as hard plastics like PLA or PETG would. This is important because I'll be testing it indoors. It has a mass of 4 grams and it fits into the barrel with minimal friction and a minimal gap, and will not have that much leakage. For the first test, I decided to only pressurize it to around 4 bar, which is around 60 psi. 3, 2, 1. So it seems to only have made a slight dent right here. It seems to have tumbled a bit, because it has made sideways mark right here. I think I'll try it with a slightly higher pressure next. Next, I increased the pressure to around 6 bar, which is around 90 psi. And this time it made a similar looking dent, but slightly deeper maybe. To almost triple the velocity and thus get almost 10 times the kinetic energy, I changed the barrel to this 2.5 meter long, 12 mm inner diameter PVC pipe. Although it's not the most optimal for velocity either, it provides plenty of performance with a fraction of the barrel length. Any longer than this and it becomes very impractical to use. I decided to first test this with the same 4 bar, or around 60 psi, as in the first test. Oh, it went completely through it. Next, I wanted to see if it could penetrate some empty aluminium monster cans. This time, I pressurized it to 6 bar, or around 90 psi, which should make it go around 150 meters per second. And it shot straight through the monster can, and completely through the hard XPS foam behind it, and got stuck in the foam behind it. Here's what the monster can looks like, and as you can see, it's completely shredded. It penetrated deep in the foam. It had almost 50 joules of energy, which is more than 4 times as much as a paintball. It would hurt. Originally, my plan was to measure the velocity of the projectiles by taking some high-speed video and seeing how many centimeters the projectiles move between every frame, but they were faster than I had anticipated, and because I didn't have any camera that could capture over 1000 frames per second slow motion, I had to forget about that idea. Overall, this was a fun project and I learned a lot, and I'm planning to upgrade this cannon to a much bigger barrel in a future video to unlock its full potential. Thanks for watching, and I wish you enjoyed this video. Be sure to subscribe, and see you in the next one.